Okay. Hello, everyone. Good morning. My name is James Lucius Sakenwa, and I would like to welcome you to the Quantum Lucius YouTube channel. Today, I'm honored to be joined by Professor Jesse Berezovsky of the Physics Department at Case Western Reserve University. Professor Berezovsky earned his Bachelor's of Science from the University of Minnesota and his PhD from the University of California, Santa Barbara. He also did his postdoc at Harvard University. He joined the crew around 2010, where he now leads a research group exploring quantum phenomena in solid-state systems, such as the interaction between electron spins and photons in nanostructures. His work combines deep quantum mechanical foundations with practical device-oriented research. He also has other endeavors such as a Catland, which is a website where he attempts to explain a lot of the weird stuff in quantum mechanics. Today, we'll be talking about the history of quantum mechanics, how the ideas have developed, what questions non-physicists might have about quantum mechanics, and how current research, such as Professor Berezovsky's, connects to the foundations. Thank you, Professor Berezovsky, for joining us today.
Thank you. Happy to be here.
Okay, so I already told you that initially I was uh the introduction that you gave about quantum mechanics at the beginning of class this semester was very interesting to me. So could you please start us off by giving us that same introduction?
All right. Let's see. So I guess quantum mechanics was developed about 100 years ago at the beginning of the 20th century. And so leading up to that, we are at the end of the 19th century, beginning of the 20th century, and we have to think about where physics was at the time. So um, there are sort of two important pieces that go into this, and one is how we understand what light is and how we understand other particles like electrons. So light, of course, has been studied for a long time. And uh, going back to, say, Isaac Newton, of course, revolutionized physics in his time in the early 1700s and really created like physics as we knew it for hundreds of years. And according to him, light was a very small particle. So a beam of light was like a stream of particles coming from the sun or from a flame or whatever. And he, worked out a lot of things about light, like how light gets bent in a prism and things like that, by thinking about light as little particles that fly through the air. And that view, was the view of pretty much everyone for the next couple of hundred years or so, maybe 150 years. But then in the late 1800s, there were some developments, specifically on the theory side. Maxwell developed his equations for electric and magnetic fields and found that you could actually describe light as a wave of electric fields and magnetic fields. And so that doesn't seem like a particle at all. On the experimental side, Young did his famous double slit experiment, where you could shine light on a pair of closely spaced slits or holes in a screen, and when those two sources of light combine on the other side of the screen, when they spread out and combine, you see this very distinctive interference pattern of light and dark stripes, which is a smoking gun that what you have going through those slits is a wave, where the troughs of one wave add up with the troughs of the other wave, or the peaks of one wave add up with the peaks of the other wave, giving you larger intensity, and other places where the peak of one wave overlaps with the trough of another wave, canceling out and giving you no light. And so these two things kind of upended this, long-standing belief that light could be thought of as these little particles. Now, the other sort of development that was going on was understanding the structure of matter at the fundamental level. And so there was already good evidence that matter was made of atoms. Not everyone believed it at the time, but there was good evidence for that. We had discovered all these different elements, and we found that they were combined with each other to form molecules, had this whole picture of how atoms came together. But what was inside of an atom? So this was a development also around that time period where they found that if you take a piece of metal and apply a voltage to it, something comes out of it. And you could see like these things hit a particular kind of like a phosphor screen and it would cause the screen to glow. That's like how an old TV works. And so what are these things coming out of the metal? Well, they were called electrons. And just like Newton's framework, where everything can be thought of as a particle, I thought, well, these are like little particles coming out of the metal, and all these particles are one of the constituents of an atom. So that's where we are. We've got light is now believed to be a wave, and electrons are these new kinds of particles that were just discovered. But there were a few problems. It sort of looks like the situation is great. We understand almost everything, but there's just like a few small problems. And then it turns out that those problems cause the whole picture to unravel and revolutionize our understanding of really the nature of reality. So on the front of light, one of the problems was this idea that if you have a box, say a metal box that's opaque and hollow, the electrons in the metal will wiggle around, and when an electron wiggles, it emits light. And the stronger it wiggles, the more energy the light has. And so, because there's some temperature of the box, the electrons are always wiggling. As you know, like if you heat up like the metal box a lot, it'll start to glow red. But even before it gets that hot, it's still emitting light just at a wavelength that we can't see in infrared. And so you could ask how much light is in the box. If you drill a small hole in the box, how much light you can measure coming out of the box. And so back then in the end of the 19th century, beginning of the 20th century, people could do that calculation. How much light and at what wavelengths should you see coming out of the box? And people could also do that experiment. And the two didn't agree. Kind of fairly closely agreed, but they did not agree. And that's always troubling. What's wrong? Everyone tries to find a solution to the problem. Maybe there was just a problem with the experiment. Maybe there's some detail you forgot to take into account in the theory. And then the sort of the key turning point here was a paper by Max Planck. And he came up with this idea that said, okay, well, the electrons are wiggling with, each one has some different energy that is wiggling with, and it emits light at the corresponding energy. But what if we just assume instead of that the electrons just wiggle at any energy, that there's only certain specific energies that each one can wiggle at? Those energies are very closely spaced. So when you look at it, it seems like they can wiggle at any energy, but there's really, instead of any energy, just very little like discrete specific energies. And if you do the math using that assumption, it comes out just right. You can match the data with the experiment just right. And why did he make that assumption? No reason. It was just like, this doesn't make any sense why this would be the case, but if we make this assumption, the data fits the experiment. And so that means the electrons only wiggle at certain frequencies or at certain energies. The emitted light only can have certain energies. And so you could call that being quantized. Instead of being continuous, they're sort of discrete levels. The energy comes in quanta or can be measured in individual quanta. And so it worked. No one knew why. And then a similar development was another question people were confused about. And this one, we'll see, ultimately was solved by Einstein. And right around almost exactly the same, very close to the same time that Planck came up with his idea. The problem here was that if you have a piece of material, like a piece of metal, and you shine light on it, sometimes if you shine enough light on it, electrons from the metal can fly out, and you can measure those electrons coming out of the metal. But what's confusing was that if you have light of a short wavelength, so the color, a certain color, so like say blue light, you can get electrons coming out. If you turn up the intensity of the light, you turn up the brightness of the light of blue light, you get more electrons coming out. But say you shine red light of the longer wavelength on the metal, you see no electrons coming out. And you think, oh, okay, well, let's just turn up the intensity. It's just not hitting the electrons hard enough. So you turn up the intensity of the red light, still no electrons. So uh, there's something weird going on here where it's not just the amount of intensity of the light hitting the material that's causing the electrons to come out, but you need the wavelength to be short enough. And so how do we explain that? So Einstein came up with a solution that's actually very similar to Planck's solution, which is that the light is not sort of this continuous thing that's coming in, but composed of individual packets of energy. And so these packets of energy, which kind of seem like particles, are flying in, and they only hit electrons one at a time. So what that means is that each packet has to have enough energy to knock an electron out of the material. So the blue, say photons, we call these packets of energy photons, just to skip to the end of the story there. So when these packets of energy are absorbed by the metal, they, a single packet has to have enough energy to knock it out. So a blue packet has enough energy to knock out an electron. And as you know, if you put more blue packets in, more electrons get knocked out. But the red packets don't have enough energy. And so you put a red packet in, no electron comes out. It doesn't matter how many you send in. If a single packet can't hit a single electron and knock it out, no electrons are coming out. So it's sort of the same idea in both cases, in a sense. There's sort of this discreteness, this quantization, where instead of things happening at any old energy, there's only these certain energies present for both electrons and for light. And so this is weird because, right, this is sort of like Newton's original idea that light should be a particle. And then they changed it and said, no, it's a wave. We see it's an electromagnetic wave. We see interference of light. And now we're going back and saying, but if you assume that it acts like a particle, we can understand these two effects, so-called black body radiation and the so-called photoelectric effect. So that's strange. And now switching to the other track of understanding electrons. So electrons were originally thought to be particles. In fact, one of the people who discovered the electrons, coming out of as these rays coming out of so-called cathode rays coming out of a piece of metal was J.J. Thomson. He won the Nobel Prize for that discovery. But just like Young was able to do the double slit experiment with light and show that light can interfere and form this interference pattern, it turned out you could do the same experiment with electrons. And it's harder to do with electrons because the wavelength of an electron is typically much smaller than the typical wavelength of light. And so the experiment has to be done on a much smaller scale, and you have to find some way of effectively creating these slits. For example, by using the crystal arrangement of atoms in a material, the sort of, in a sense, the space between the atoms you can think of as the slits. And so by doing experiments like that, there were two groups, one Davison and Germer, and the other George Thomson, who happened to be J.J. Thomson's son. Both showed that electrons, just like photons, can interfere with each other and therefore act like waves. So in both cases, we have this sort of going back and forth. We have Newton saying it's a particle. We have Young and Maxwell saying it's a wave. Then we have Einstein and Planck saying light is a particle. And in the case of electrons, we have J.J. Thomson discovering that there's this new particle, the electron, and then these other people, including his own son, saying, no, it's a wave. We see that there's this sort of like big confusion starting to emerge. And so that's the stage on which quantum mechanics starts to develop. So whenever there's a big change like this in our understanding of physics, when we look back on it, we tell it like this nice story of discovery. But in reality, I think it's a much messier process where there's a lot of confusion and people are putting forth all sorts of ideas, and many of them don't work, and some of them sort of work, and then some of them that sort of work get fixed a little bit, And then eventually what emerges is our new framework of understanding. And so it's a little bit difficult to trace exactly how things develop, but a few of the key developments was a guy named De Broglie, who said, well, maybe everything is a wave. Maybe electrons are waves and photons are waves, and we can understand their momentum and their energy in terms of their wavelength and their frequency. And various things seem to kind of hang together. One of those things that hang together in that picture was the light that's emitted by atoms. We all know that if you heat up a material, it can emit light. And in particular, if you heat up just like a gas of atoms, it can emit very particular colors. Like if you have a sodium lamp or a neon lamp, they emit particular colors depending on what kind of atom you have. And so this was another very confusing thing at the time. Why should atoms emit light just at specific colors? We have this picture of an atom where you've got these electrons in there. The electrons are flying around, they're wiggling. Wiggling atoms produce light. Again, just like with the black body radiation, the radiation inside the box, they could wiggle at any frequency. They could emit light at any frequency. And as they do, as they emit light, the electrons should lose their energy and eventually settle down. But it seems like they never do. They only emit light at certain energies and never lose all their energy. And so this is another case where this new wave idea can start to explain things. Because if you think of the electrons not just as little balls flying around in the atom, but as waves traveling around, if a wave goes in a circle, uh, wavelength has to be a integer fraction of the circumference of the circle. In other words, if you go around the circle, there has to be a whole number of waves. Otherwise, the beginning of the wave won't match up with the end of the wave. And so that idea tells us that if you have if you have electrons circling around the nucleus of the atom, then they can only have specific orbits. And that allowed us to really understand a lot about why atoms behave the way they do. And so the idea is starting to kind of coalesce. And then all we need from there is an equation. Like, okay, we've got these waves. What's the mathematical equation that describes these waves? And there was a lot of, toying around with things, trying to figure out, okay, we needed to agree with everything we already know, but we need some sort of equation to tell us how these waves come about. And finally, Schrodinger came up with such an equation by sort of just playing around with things and found one that worked. And that sort of gave us the quantum theory that we have today. Of course, there were some very strange things about this wave equation. The waves that it describes require the use of imaginary numbers, which is very weird. Imaginary numbers are often useful for doing things in a practical sense, but in the end of the day, the imaginary part of the number always goes away and is just sort of a helpful numerical mathematical trick. But in this case, it seemed like the imaginary numbers were really important, and the imaginary part of the waves had some physical reality in a sense. So that was a weird thing. And the other weird thing was like, it's nice enough to say that everything's a wave, but when you look at things, they certainly don't seem like waves. They seem like particles. Like that's why Newton thought everything was a particle, and that's why it worked so well for Einstein and Planck to hypothesize that maybe you could describe light as a particle. And so there's something also weird going on here. And that sort of the solution they came up with was that things act like a wave. You can describe a particle of matter or light as a wave. But then there's this thing called a measurement. A measurement is the only way you can look at something. You can't see these waves. All you can see is what happens when you measure them. What does it mean to do a measurement? they didn't know. It's still a little hazy. But if you assume the only way you can ever find out about something is by measuring it, then you add this extra bit that says when you measure something, the wave suddenly collapses and turns into something that looks more like a particle. If you measure the position of of the particle, the wave collapses and becomes very narrow, just as it would if it were localized in one spot, and becomes particle-like. And so that was kind of the picture that emerged in the early 20th century. And it had these very weird features, like uh, this role of complex numbers and the fact that you can't actually um, see the waves, but have to perform a measurement on them. And then what happens when you perform the measurement is that the outcome that you observe is uh, only decided by probability. It's a roll of the dice. There's random chance. Normally, random chance means you just didn't know what the outcome was. Like if you have if I say, I've got a penny in one of my hands, which hand is it in? You might say, well, there's a 50-50 chance it could be in either one. But of course, it is in one. I know which one it's in, but you don't. And so the probability is used to understand your own lack of information. Likewise, if I uh, roll a die, I don't know how it's going to land, but that's just because I don't know the specific trajectory that the die is taking, or the surface of the tabletop that it's going to hit, and all the imperfections in it that will cause it to go one way or the other. In principle, a sufficiently intelligent and well-informed observer could figure it out. But according to this new theory of quantum mechanics, things work in a different way. Things are really fundamentally random. And in fact, Einstein didn't like that and said something to the effect of that God does not play dice. In other words, we play dice because we don't know how the die is going to land. But but the fundamental laws of the universe shouldn't be random. They should be deterministic. So this was a weird thing. Uh, and there's even weirder things. There's even weirder things about what happens when you have multiple particles and or multiple different characteristics of a single particle, and you get this phenomenon called entanglement. And that was another thing that Einstein pointed out, along with Podolsky and Rosen, in a famous paper they called the so-called EPR paper, where they pointed out that there's an apparent paradox, according to them, something so strange that it couldn't possibly be true when you have this entangled properties. And so that was sort of the state of things in the early 20th century. This theory, and I should point out the theory worked really, really well. Like it revolutionized the understanding of many things. For example, chemistry. Why do we have all these atoms? We have the periodic table with like 100 some atoms on it. Why? Why these specific ones? And why not others? And why do those atoms have the properties that they do? Before quantum mechanics, it was basically an exercise in just tabulating all the different atoms we could find and what their properties are. After quantum mechanics, we could actually understand why we have these atoms, predict what their properties should be, even predict the properties of new atoms that hadn't been discovered yet, and just predict the properties of new materials that hadn't been made yet, and things like that. So the theory worked in many, many ways very, very well, and really led to the revolution in technology that we had in the 20th century. So these other questions, like this nature of entanglement, this nature of measurement, these are questions that we're starting to unravel now, and they're leading to the technologies of the 21st century, such as quantum computing. Maybe I'll stop there with my introduction and let you say something if you have a follow-up question.
Okay, yeah, thank you. That was very nice to listen to. I took down a couple notes um to ask a couple questions so that I won't uh intervene with your train of thought. Um, so basically, first thing I'd like to ask is, the nature of superposition. Could you please explain superposition?
Sure. Yeah. So that's something, a term that's often used when talking about quantum mechanics, that uh, something doesn't just have to have a single property, but can have a superposition of two different properties, two different, in a way, two different things at the same time. Now, in a way, it's not surprising. Um, the surprising thing is that matter can be described as a wave. That's surprising if you think of just a chunk of matter as a bunch of little particles or balls or something. Um, but you know, experiments have shown with great accuracy that in fact we can describe matter as a wave. And so if you have a wave, like you could imagine any wave, like a wave on a string, like a violin string, or a white wave in water or something like that, the wave doesn't just have to have, the wave doesn't exist in just a single position. It's spread out over many positions. And so in that sense, you could think of a wave as being, a long string with a little bump here, and then a little bump here, and a little bump here, and a little bump here, all added together to give you the full shape of the wave. So in a sense, that's you can think of the wave as a superposition of little bumps in many positions. But you could think of it as other superpositions. For example, you could think of it as um, uh, you have a wave could have multiple different wavelengths in it. If you pluck a violin string, it doesn't just give you a wave at a single wavelength at a single frequency. It gives you waves at many different frequencies that produce the sort of richness of the sound. And so you could think of that as a superposition as well. And so it's a wave. If you fix the ends of the violin string, there's a wave that wave has to have zero amplitude at the two fixed ends. So you could have a wave that has one sort of hump, or you could have a wave that has two sort of humps or three sort of humps. And those can all be there at the same time, adding up to the full wave of the string. And so in a sense, you could think of that as a superposition as well. If you start really thinking in terms of waves, the idea that things can be in a superposition, you can think of the wave as adding up a bunch of different waves, is not that weird. Like I said, the idea that matter is a wave to begin with is weird. And the fact that, um, and then the other weird thing is what happens when you measure it. And so that's, I think, what often gets people about the superposition idea is that when you measure it, you wind up only, you only see, you can describe something as a superposition, and then you only wind up measuring one of the pieces of that superposition. Uh, and that's this weirdness of like the so-called measurement collapse. And so I think that the measurement collapse is what makes it seem weird. So for example, if you had a violin string, and it's vibrating at multiple different frequencies, and multiple different wavelengths, that is a classical, not you don't need quantum mechanics to understand that vibration, and you can hear all the different frequencies. That's what happens when you hear it. The rich sound is hearing all those different frequencies at once. But if a quantum wave, you can't see all the different frequencies at once. If you try to measure the frequency, which is the same thing as measuring the energy, you only that you get this weird effect of like this probabilistic collapse of the state, and you only see one of the energies. And so that sort of gives us this confusing intuition, because it's like when you measure it, you're like, well, it has this one energy. That was the energy of the thing. But the quantum description is actually it had multiple different frequencies. And then when you measured it, it picked out one of them. And so that I think is why it seems strange to us that you should be able to describe something as a wave and a superposition of different waves. When you measure it, you only see one of them.
Thank you. Yeah, thank you. You've mentioned before that you support the many world interpretation of quantum mechanics. Could you please explain the interpretation and what it has to say about the measurements problem and the superposition?
Right. Yeah. So like if you the many worlds, or so some people prefer to call it the Everett interpretation after its inventor. Um, so as I've been describing, like so Schrodinger came up with this wave equation that described these waves that can be used to explain uh, a lot about nature. But then there was this problem of measurement. Like, okay, but why is it that when we measure something, you only see like one thing and it's random? And to me, that whole business of measurement seems highly implausible. Like, as Einstein said, God doesn't play dice. Uh, like, there's no physical mechanism of why the wave function changes that we know of. And so it seems weird. And so the question is, do we need it? Maybe these waves, as given by, as described by Schrodinger, can explain everything we see, including measurements. How could that be possible? Well, if you have something you want to measure, you need to use a measurement device. If you have an atom, a radioactive atom decaying, you can use a Geiger counter to see if it clicks. And, that counts as a measurement. But, the Geiger counter is also made of atoms, and those atoms should also be described by a wave, by the Schrodinger equation. And so why can't we just describe the whole process of the atom you're measuring and the device that you're using to measure it all as a wave described by the Schrodinger equation? That sounds pretty reasonable. If the theory applies to the atom that we're measuring, why should it not also apply to the atoms in the device being used to measure it? So why not? Why don't we just try to solve those equations? Well, the problem is that those equations are incredibly complicated and difficult to solve. When you have a single particle, like a single electron, you can solve Schrodinger's equation in some cases, some select few cases. If you have two electrons, you can solve Schrodinger's equation in even fewer cases. Uh, the reason why it's so hard is because of this phenomenon of entanglement. When you have two electrons, you can't just treat them separately. Regularly, you think of two particles, you can think of each one's position and each one's momentum and just see how they move around and maybe they hit each other and bounce off, whatever. But when you have entangled states, there's many, many, many more states you have to keep track of. And so it becomes very hard even for two or three or four electrons to figure that out exactly. It even becomes extremely hard for a computer to simulate. Just the amount of memory it would take to store the information about all of these different entangled states is so large, it just becomes utterly impossible for any computer we have to be able to do it. So that's why we can't just, easily turn the crank and see what happens when the atoms in the Geiger counter interact with the particles that you're trying to measure. But there's sort of ways to look at it and to reason about it. And the picture that sort of emerges is that what happens when you measure something is that the measurement device becomes entangled with the thing you're trying to measure. And so a point I like to make about entanglement is that entanglement is not an unusual phenomenon. It's incredibly common. It happens all the time to the particles around us, in the air, in our bodies. Everything becomes entangled with everything else. The trick is if you want to not have entanglement, to avoid it or to get it just in exactly where you want it. And that's the ability that's underlying our ability to now start to make quantum computers, is that we don't have to just settle for this inevitable soup of entanglement. We can avoid it. We can create a system that has very little entanglement and then introduce the entanglement just where we want it to create a very particular quantum state. But so back to measurements, the idea is that when you have a system that's simple enough that you can describe it by quantum mechanics in a sensible way. It interacts with this much larger device, this measurement device, and the states of your simple quantum system you're trying to measure become entangled with the states of the measurement apparatus. So the measurement apparatus might have um, a pointer on it. Like you're trying to measure, is the particle on the left or the right of my device? And if it's on the left, the pointer might go like to my left, or to my right if it's on the right. And so the idea is that if the wave describing the initial particle could be thought of as a superposition of a wave on the left side and a superposition on the right side. So some waves over here and then some waves over here. Then what happens when you measure it, when it interacts with the measurement device, is that it becomes entangled with it, and the entangled state can be thought of as having two parts to it. It can have a part where the electron waves are on the left and the pointer is pointing to the left, and then another part of the wave where the electron waves are on the right and the pointer is pointing to the right. And the trick is that when this entangled state becomes so massive, when it has so many particles, like the measurement device might have 10 to the 23 particles in it. And in fact, the measurement device also interacts with all the air molecules in the room and the photons in the room and everything. So many, many particles are interacting with this, and when they do, they all become entangled. The trick is that what happens is that you can have two parts of the wave function that become very well separated from each other. What do I mean by separated? I mean that they never overlap and give you this interference. If you never have interference, you never had this problem to begin with. That was what opens up the whole can of worms, like with Young's double slit experiment. You thought you had particles, everything seemed nice, and then it was like, wait, but they're interfering with each other. That tells us something weird is going on. So the effect here is that when you get these particularly like entangled states with large numbers of particles, those two different parts of the wave function will almost certainly never interfere with each other again. And everything will play out within each part of that wave function as if the other one doesn't exist. So that means you have these two parts of the wave function, one where the pointer is pointing to the left, one where the pointer is pointing to the right. And you could just figure out how that wave is going to change going forward by completely ignoring the other part of the wave. So you just take the one where the pointer is going to the left, and you say, what else could happen? We could have a computer record the position of the pointer. Now the memory of the computer will store the information. Pointer is pointing to the left. Then maybe you will look at the pointer. How do you do that? Well, photons bounce off the pointer. Some of those photons go into your eye, and they interact with the atoms in the retina of your eye, which send signals through the nerves of your optic nerve into your brain. Store things in your memory. Oh, the pointer was pointing to the left. So in that part of the wave function, all these things play out. You perceive the wave function. You perceive the pointer pointing to the left, telling you that the particle is on the left. But in that other part of the wave function that has no interaction with the other part, so it evolves completely independently, there's different things that play out. In that part of the wave function, the same photons come in, bounce off the pointer, but now the pointer was in a different position. So different photons bounce off that pointer, go into your eye, trigger different atoms in your retina that correspond to you seeing the pointer going the other way. So we have these two different parts of the wave function, and I've said there's almost no chance they'll ever have anything to do with each other again. They just play out independently. So why do we consider those as separate worlds? That's a convenient way to think of these different parts of this incredibly complicated entangled wave function. If they never have anything to do with each other, why not just focus on one of them and forget that the others exist for now? And that's a world, that's a timeline playing out. Meanwhile, there's other timelines playing out in these other parts of the wave function. So indeed, that means that at least in certain circumstances, there are different versions of you seeing different things. There's a version of you perceiving the pointer pointing to the left, and there's another simultaneously another version of you seeing the pointer pointing to the right. And so really all it is we're taking this equation developed by Schrodinger and saying, what happens? What happens if we see what does that equation predict? And like I said, we can't do the math exactly, so we're not 100% sure. But what it sure looks like is that it predicts that this wave function should develop these separate parts that don't interact with each other. And you might as well think of those different parts as being different worlds.
Oh, That was that was hard to swallow. So the concepts of different worlds is difficult to grapple with. Is it like multiple universes or just one universe?
Yeah, I mean, you could think about it in different ways. I think that um, I would prefer to think about it as saying it as one universe, but that different things can happen simultaneously within that universe. So this is going back to your question about superposition. Uh, I claimed that it's not weird. That if you have a wave, the wave can be doing one thing over here and it can be doing something else over here. And you could have a string and there's a little wave propagating over here and another little wave propagating over here. And so in that sense, it's not weird. One thing I didn't really mention is that another weird aspect, well, this is what leads to the idea of entanglement, is that if you have two particles, they don't each have their own wave. They both are a part of one larger wave. And so taking that to its logical conclusion, there isn't multiple wave functions for every particle in the universe. There's one wave function for all the particles. And it's a very complicated wave function because of the presence of all these entangled states. And so the idea is that within this wave function, um, it's not, it can have this property of superposition where uh, if you think about it classically, it's like multiple things are happening at the same time. So in one part of the wave function, a ball could be rolling to the left. In another part of the wave function, that same ball could be rolling to the right. Um, and the two will have nothing to do with each other. They could pass right through each other um, because they're in completely separate parts of the wave function, even though to us they represent a ball in the same position. So it's sort of a misconception of what the many worlds interpretation says is that like when some branching point occurs, when a ball could roll to the left or the right or something, like there's like suddenly another universe gets created somewhere else. That's not what happens. It's one wave function, and what happens when there's a branching point is that you get these sort of two separated parts of the wave function that both exist in the same three-dimensional space, but represent different outcomes occurring, sort of overlapping with each other.
Okay, that makes more sense. But then going from a wave being like a superposition of different waves to the wave function describing multiple uh, events occurring simultaneously, it's difficult to like picture exactly how those multiple events occur or exist simultaneously and how we are only able to view one of them because we are part of the wave function and it's also describing what we are doing too. So the world that we perceive is basically just one of the coherent states of the wave function. and it's possible that we could be perceiving the other one. It just, but why do we have to perceive only one of them?
Well, it's very confusing. I agree. And in fact, I mean, uh, the issue here is that we're getting away from uh, things that we can solidly understand and getting into the idea of like our own consciousness and our own perception of reality. And so those are hard questions to answer. But I think what really helps is to step back and think about, I mean, what the first thing to do is to think about like a single particle, and then to think about two particles, and then to think about three particles. And that we can start to, simulate on a computer and see what it does. And so you can use simulations like that to see how, um, say, um, so here's like an example. I'll try to just illustrate it using my hands. Say you have three particles. One particle is sitting here, one particle is sitting here. It's really a wave, but it's a wave that just has like some amplitude here, and this one has some amplitude here. Two particles sitting here. Our third particle will be in a wave that's a superposition of being over here and here. So, farther out. So this is, my hands now represent a single particle. It has a wave that has some amplitude here, nothing, and then some more amplitude over here. The question is, if these two different parts of the superposition start moving this way, and these particles are such that they repel each other when they hit each other. So like they're like billiard balls, so like you've got your two particles here, and you're one particle in a superposition here, and they both move in, they're going to collide, and they're going to start these ones moving. What happens when this particle and this particle meet? What happens is they go right through each other. Uh, that's surprising, but that's what the Schrodinger equation predicts. Um, because um, what you can think of the Schrodinger equation as, I'll try to explain a little bit. Um, it's sort of a number. It's a complex number, meaning it has real and imaginary parts, but no matter. Um, a number associated with every possible position of the particle. Um, and according to the usual interpretation, the bigger the amplitude of that wave, the more likely you are to find the particle at that position. But if you have two particles, what the wave function is a number that gives you an amplitude for every possible pair of positions. So as I said, it's not two different wave functions that gives you a single amplitude for the particle of one position and then another amplitude for the particle of the position of the other particle. It's a number for every pair. And so if you want to think about drawing it as a plot, you don't make two plots for each particle, you make one plot for both particles. Even just if each particle only moves in one direction, one dimension, you need two dimensions to draw all these amplitudes for two particles. If you have three particles, the wave function is a number corresponding to every possible triple of numbers, every possible triple of positions of the particles. So it's like if you want to draw those, you need a three-dimensional space just to capture the motion in one dimension. So really that's the space in which this wave function is playing out. If you have a million particles, it's very hard to imagine, but you have to imagine a space with a million dimensions. And that's the space in which you can imagine this wave function moving around. And so without going into any more detail that I need to, the idea is like with these two balls that get hit by a single ball in a superposition, why don't these two components of the wave function collide? It's because even though in three-dimensional space that we're looking at, they're meeting in this much bigger dimensional space in which we can describe the wave function, they're nowhere near each other. And so they don't interact with each other. And that's the idea of the multiverse, is that you have this enormously large dimensional space And so part of the wave function could be off in some corner of it, and the other part could be off in some other corner. And think that in three-dimensional space, things could be overlapping, but within this space that we can describe the wave function, they're nowhere near each other. So that's boiling things down to sort of a few particles. We can see things like simulate things, and you can see, uh, you know, indeed, a ball can be doing one thing in one part of the wave function and another thing in the other part of the wave function, and those two can overlap in space and move right through each other without knowing they're there. So we don't want to know just about three electrons or something, though. We want to know about macroscopic stuff that we see in our everyday lives. So, like, we could think about our own brain, but that's confusing. So you could take it a step not as far and think about maybe just like a computer memory. We're much more comfortable thinking about a computer memory as a deterministic mechanical system, whereas maybe our brain is, you know, more likely to have some sort of metaphysical interpretation or something. So if you imagine the situation again now where we're measuring a particle and a pointer is going to the left or a pointer is going to the right, um, you could think about a computer recording the outcome of whether the pointer went to the left or the right. And uh, as I said, it's sort of like in each of those parts of the wave function, each one plays out like its own independent timeline. So if the particle goes to the right, whatever sensor the computer has to measure this motion of the pointer um, sends some electrical signal down a wire. It goes into the computer. Uh, those electrical signals get stored in the computer's memory. Maybe there's a hard drive where some magnetic elements get flipped from one to the other. So it's all a physical process. And so it all makes sense. It should all just occur due to, um, the laws of physics. And then I said in the other part of the wave function, this other timeline is playing out it's in the same physical space, uh, in three-dimensional space, a different part of the wave function though. And in that case, the computer does something different. Say that magnetic bit in the hard drive that was flipped one way to represent the pointer going left is flipped to the right, uh, in this other part of the wave function. And so now you could say, well, can the computer represented in one part of the wave function ever know that there exists another part of the wave function where something else was recorded? And the argument is no, it cannot know that. There's no possible way it can have something that happens to it that depends on what's going on in that other part of the wave function. And the idea is that they become so separated in this really high dimensional space that one can never have any influence on the other. And so what could you try to do? You could say, well, let's have the computer double check its memory. Go back and read that bit and display on the screen what's the status of that bit. And it would tell us pointer's pointing to the left. In no way could it ever say, also the pointer's pointing to the right. And so in that sense, everything in that part of the wave function will play out as if that was the only thing that happened. And then you can ask the question, is there any difference between what's happening in that computer, taking in data through some sort of sensor, storing it in its memory, processing that data using its processor, and what happens in our own brain when we take in information through our senses? It stores that information somehow in our brain. We somehow process that information. And so the idea is that this timeline playing out that corresponds to one version of your own consciousness can only ever be aware of the outcome of the measurement in that part of the wave function and cannot be aware that any others exist.
I think I'll need a little more time to understand that. One problem, or rather, one question I had in the quantum mechanics was uh, the electron in the atom and how there are discrete energy levels around the nucleus. and the electron can only exist in one of the energy levels at a given time. So for a superposition, for an electron to be in a superposition of energies, or rather, before we even get to superposition, how does an electron absorb energy and go to a different energy level, or release energy and go to a lower energy level without crossing the barrier between the energy levels?
Hmm. Um, that's a good question. Again, I feel like there's a lot of confusion surrounding these questions. And the confusion often stems, I think, from the fact that quantum mechanics is so hard, uh, and mathematically. And like I said, we really prefer to think about quantum mechanics of single particles. Um, because well, even adding a second particle makes everything so much more difficult to calculate and so much more confusing. And so when a electron, say, changes its energy in an atom, it's because it's interacting with another particle. It either emits a photon or absorbs a photon, or it gets, you know, smacked into by another electron, and that electron loses some energy, and this one gains some energy, and so forth. And so one thing we know is that the energy is always conserved, right? So the total energy stays the same, but in the entire system. So if a photon is emitted and carries away some energy, the electron loses energy, but the sum of the two always stays the same. And so that means if you think about the wave function for both particles, actually the energy didn't change at all. And as we have been talking about, you can't think about two particles as having separate wave functions. So it's not like the wave function of one gets a lower energy and the other one gets a higher energy. Um, it's a single wave function and its energy is constant. And so it's a slight fiction to say that actually it's the energy of the electron has changed. Uh, Really, what you're doing is you're kind of deciding how to partition up the energy of the whole system and say, okay, this energy belongs to an electron and this energy belongs to the photon or to another electron or something. Um, and really, what energy is in quantum mechanics is the frequency of the wave, how fast it's wiggling. And so whenever I say energy, we could instead say how fast the wave is oscillating. And so that means the wave function is just oscillating at some constant frequency. And uh, what's changing is the spatial arrangement of the waves. So what's happening is like you have a wave with a long wavelength, say, uh, and then the photon is emitted. As the photon is being emitted, the wave starts getting a component in it that has a shorter wavelength. And so those wavelengths have to be fixed because if it's confined, like I was saying, like if you have a string fixed at both ends, you can only have certain waves. It can only be a one hump or two humps or whatever. Um, and the same thing goes for an electron and an atom where the wave has to go around in a circle. You have to have a whole number of waves around the circle. And so as the shape of that wave starts changing, all it can do is get a little bit less of one wavelength and start getting a little bit more of the other wavelength or multiple other wavelengths or whatever. Um, there's no other option. And so that is why you sort of interpret um, when you're thinking about how do we divide up the total energy, you think about like, well, uh, if this if this wave existed by itself and the photon wasn't part of the wave function, that would be a higher energy wave. Um, and so in that sense, the way to picture, if you want to ignore the photon as we usually do, or ignore the other thing that's taking the energy away or adding the energy, what's happening is you have your particle in some wave. Uh, at some frequency, and then it starts getting like a little bit of another wave. It's still got its wave here, but it's getting a little bit of wiggle at a higher frequency. And so that frequency starts to grow and the other one starts to shrink. And at no time is there ever any intermediate frequency. Um, it's just that there's only two frequencies, and the amplitude of one shrinks and the other grows. And if it wants, one could go all the way down to zero, and the other one could go all the way up to some maximum height. And then you've gone from one frequency to another. Just looking at the atom, remembering that actually the frequency of the combined system just stayed the same.
Okay, okay. Uh, Thank you for clarifying that a bit. Um, so if all of these interactions causes branching, how then is it possible for us to isolate and manipulate the wave function of certain particles? Let's say, for example, in quantum computing or quantum sensing, how can we manipulate that wave function, or rather, quantum properties of those particles if we are in one branch of the universal wave function?
Right. So first of all, it's very hard. That's why we're all, it's such a struggle to build quantum computers. Um, and so first of all, the idea is that, yes, okay, there could be this universal wave function that has many parts. We perceive ourselves to be in one branch. And so you can proceed as if that's the only branch. Like, you don't have to worry about it, that there's these other ones. And I would recommend not worrying about it. Um, and so if in this branch you see a particle in a particular, well localized position, you're free to just consider that as being where it is. And don't have to think about, oh, but there's actually more of the wave function somewhere else that I have no access to. Doesn't matter. Because however things play out in this branch, it will play out as if that was the only thing. So, so that's your starting point, is that you can have you're perfectly free to consider your branch as the only one. From there, you have to make sure that you don't get any entanglement you didn't want. And entanglement will occur anytime two particles that have some distributed wave function interact with each other. Pretty much anytime two particles interact with each other, some entanglement is generated between the two particles. And so you really have to control all interactions between the thing you're trying to control the quantum state of and everything else. And so often that means you want your qubit to be very small. I should define a qubit. A qubit is the fundamental element of information in a quantum computer. Like a bit is a zero or a one in a regular computer. A qubit or a quantum bit is like a zero or a one in a quantum computer. And so that's like the thing that has, some wave that we want to have in a particular state, and not get entangled with other stuff. And so there's a few tricks. One is you usually want it to be very small. So maybe it's a single atom. That's one kind of quantum computer where each qubit is formed by a single atom. Um, the exception to that is superconducting qubits, which have had great success actually, which was the subject of this year's Nobel Prize, was finding a fairly macroscopic system that still can behave quantum mechanically without too much entanglement with its environment due to the strange properties of superconductors. But often you want it to be small. You might want it to be a single electron or a single atom, because it just gives less target for things to hit. Anything that hits it can cause this unwanted entanglement. So the bigger you make, it's sort of a catch-22. Like if you if you have a regular computer and you want to store information in a bit, you worry about that bit getting accidentally flipped. If you make it too small, it's easier for something to come in and mess it up. If you make it really tiny, a nanometer sized transistor, a little voltage fluctuation could come in and mess up the state. Or if the best thing to do is you want to store information in a switch, you make a giant like Frankenstein style switch, that you have to like really flip from one side to the other. It would be hard for anything to come in and, accidentally bump it and change it from one thing to the other. But the opposite thing happens with entanglement. The bigger it is, the easier it is for things to become entangled with. So that's why you really often benefit from making a quantum bit small, microscopic. At the same time, you still suffer from things accidentally coming and bumping into your qubit or whatever and messing it up. So you need to avoid entanglement, but you also need to have very low noise environment. And so what that means is usually you need the quantum bits to be completely isolated from everything. So it could be very low temperature. A lot of these quantum computers, if you see pictures of them, look like these giant, enormous contraptions where the actual chip doing the quantum computing is just a usual like computer chip size thing. All that stuff is just to cool the chip down to a few thousandths of a degree above absolute zero. And so when you cool it down, you've got less things flying around and jiggling and potentially either disturbing the state of your qubit or becoming entangled with it. In other cases, you need to get a really good vacuum. So if your qubits are single atoms, you can have a single atom kind of suspended in space, held by lasers, for example, or by electromagnetic fields. So if you have a single atom floating in space, you can't have other atoms around bumping into it all the time. So you need to get a really good vacuum such that there's almost no other atoms around. So that degree of isolation is one aspect of being able to control the state. And sometimes you can just be very clever and you can find a kind of system that in some way doesn't interact with things very much. And so spin, the magnetic property of a particle, to some extent satisfies that. So trying to create a quantum bit using the magnetic polarization of a particle helps to some extent in that it doesn't really matter if another atom bumps into it as long as it doesn't change the direction of the spin. Or even more clever things where they can really try to engineer very clever quantum states that are somehow immune to disturbances from the environment. So that's sort of the approaches people are taking. I'll mention one other one, which is that you can use particles of light, photons, to store quantum bits. Photons don't interact with things very much at all, as we know, they'll go right through a window with no trouble, whereas we cannot. So in that sense, a photon can make a very good quantum bit. The drawback is that because they don't interact with anything, they're hard to control. They're hard to make them interact with each other because the first step of the quantum computing is getting a quantum system that avoids getting entangled with everything else immediately. But then the next step is to controllably create entanglement just where you want it. And so you can create these really complicated entangled states. And instead of just making use of the three-dimensional space that we're used to, you can make use of this incredibly high-dimensional space of entangled states that I was referring to earlier. And so in order to do that, you have to be able to really control interactions between the particles. And photons don't interact with each other very much. So that's the issue there, is that you have to find ways to get the photons into these entangled states just where you want them. And there are ways to do it. And so that's another approach people are working on.
Okay, thank you. It's been a pleasure speaking to you about quantum mechanics. Very interesting stuff.
Well,
I
I
have
love
to
to
go
talk about
back.
it. Thank
Yeah,
you for giving me the opportunity.
yeah. So one last thing before we go. Do you like have any advice or message to anyone out there trying to understand quantum mechanics?
Well, I would say, keep thinking about it. Um, I think I wanted to mention that, I gave sort of my own thoughts about the many worlds interpretation, but that's not the only thought out there. Um, there are other approaches people take. I find the many worlds interpretation to be the most satisfying. Um, but it's not a settled question. So there's still a lot of thought to be done. And I also think it's one of the most exciting things we can think about because it really touches on what's the fundamental nature of the reality that we live in. And we don't know what it is. Uh, my view is that whatever it is, it's probably very different than the reality that we seem to perceive through our senses. And so trying to understand that is one of the most intriguing things, I think. And it's a very interesting time to be thinking about it because with the development of new quantum technologies like quantum computing, it's really the first time that we're able to manipulate these systems in detail at this quantum level. And I think that's giving us a lot of new insight because for the first 100 years of quantum mechanics, essentially, uh, everyone knew about this entanglement stuff, and it was there, and everyone was a little bit disturbed by it, but there was no way to actually see it or do measurements on it, and so it was easy to kind of ignore. Uh, but now that it's actually forming the basis of a new kind of technology, we have to grapple with it, and we have to understand what does this mean? And uh, it's definitely a real thing because there are these devices that are operating based on this principle. And so, for that reason, I find quantum computing super exciting, just because it's the first realization of some practical thing making use of this bizarre nature of entangled states. And the other side of it is that quantum computers themselves might allow us to understand this better. Just as quantum mechanics is very difficult to calculate for multiple particle systems, quantum computers might help us do that, and in a sense, help us understand their own nature. Um, And so, I think while the field of quantum computing is often really overhyped, and I encourage everyone to take all the quantum computing news with a grain of salt, I think it is an extremely exciting time to really advance our understanding of what is the nature of the universe that we inhabit.
Okay, that was very inspiring. Thank you. Yeah, it was a pleasure speaking to you. I hope you have a great day and thank you for joining me today.
Thank you. Same to you.
Thank you. Goodbye.